Chapter 6: Distributed Forces, Centroids and Centers of Gravity. Part A. In this chapter, we will divide it into three parts. Part A is a center of gravity of a 2D body. Part B, which is determination of centroids by integration, and finally in Part C, which is distributed loads on beams and center of gravity of a 3D body. Part A, center of gravity of a 2D body. In Part A, we will cover centroid of an area, centroid of a line, first moments of area and lines, and finally we have a sample problem. We have a cylinder here, whereby this cylinder is a symmetrical in terms of x, y, and z direction. And if you compare to this 2D shape, the centroid is basically in the symmetrical dimension, whereby the point about the entire line, area or volume is assumed to be concentrated. For the center of gravity, basically defined as a point about which the entire resultant weight of the body is assumed to be concentrated. Okay, as you can see in this diagram, for this shape, let's assume as a center of area or centroid, we call it centroid. Here is located here. Once if we put extra weight at a certain place, this position, it will produce a different location of center of mass. So from the before we put the weight, the center of mass and the center of area or centroid is the same location. After we put additional weight, so it will produce a center of mass is move a little bit far from the center of area or centroid. So at a certain condition, the center of area or centroid is not the same as the center of mass in terms of location. Some of the basic or common shape of we can determine the center of gravity or the center of mass or the or centroid actually. So in this case, we have a several shape that we can basically see whether this is a symmetrical in certain axis. Okay, in this case, we have a rectangle. So it's basically x and y axis is symmetrical. So in this case of triangle, we can see only x axis is symmetrical, but y axis is not symmetrical. So from there, we have a formula to determine the location of x bar and y bar. For the case of a rectangle, we just divide the length of each side by 2 and it will produce the value of X bar and Y bar. Okay, and also it, we will use the formula for the common uh, shape. For the uncommon shape like a unregular shape, so it will be very difficult to use this formula, so we need extra additional uh, calculation, additional step or method to settle this problem in terms of determining the centroid. So for the homogeneous shape, whereby the different shape as a previous shape, symmetrical shape. So let's say we have a homogeneous, we want to look at the center of gravity of a plate. So let see in terms of weight force produced at the point of G. So at that position, we will have the coordinate of X bar and Y bar value. So basically, if you can see, the non-homogeneous shape basically is consists of many particle. Okay, many particle which is uh, produce a force, a weight force, different value on the spot of the particle position, whereby the particle also with the different shape, a tiny shape, and at a different uh, weight. So basically, if you look at the delta W1, the position is somewhere like this. So we can determine the position of X1 and Y1. So it also happen to all of the place of the position of this point, whereby the weight force is acting the value of delta W2, where the position is X2 and Y2, and also happen to others point whereby we can see this value of coordinate of position in X3 and Y3. So if we sum up all together, okay, into a value of delta W n, and also it will produce a xn and yn. So finally we will have is something like this. We will sum up to get all together, and we will have something like this, the summation of x delta w in terms of the moment at y axis. So from this, the value of a moment along the summation of all moment at point at end point, it will produce the summation is something like this. And finally, the summation basically can be represented as a concentrated force, whereby can represent is something like the integration of x dw. So it also happened to uh, the the value of concentrated force, whereby this value can be represented as a one value of w. So if we look at the moment at y axis here, we have the weight force, and the distance is x bar. So the value of moment at point y at y axis is something like this, and this value basically the same as this value and also this value. And finally, we can use this equation to get the x bar for the representing of the point of G at x axis here. So it also happened to the moment at point X. So in order to get the value of moment at point X, so the process uh, can be done by using this equation whereby the value of y bar k and w is equal to summation of y delta y equal to integration of y delta w. So in order to get the y bar, basically we will use something like this, and it also happen to the x value. So in order to get at coordinate of x bar and y bar, basically we will use something like this. Okay, this is for the non-homogeneous. If we have a homogeneous shape, like we have a common shape, maybe it's a rectangular triangle, so we basically don't use this kind of uh, integration, okay, whereby we will determine by using the summation, this summation only. Okay, later on we will see by using this one. Okay, the center of gravity of a wire also is something like this. It note that the center of gravity G of a wire is usually not located on the wire, but basically is offset from the wire line. So in order to get the value of center of gravity for the wire, the previous formula can be used. Okay, and then we proceed for the centroid. Just now we look at the center of gravity. So this one we want to look at the centroid of an area. Okay, basically the centroid of an area, uh, the formula basically they use the same as center of gravity, but a little bit changes in terms of W weight value or area, we will change to the A. Okay, so this is the initial equation produced from the previous center of gravity. So in terms of delta W, basically we want to change the value of uh, weight force by using the gamma T delta A, or we have W equal to gamma TA, whereby the gamma is basically the specific weight, or we have a weight per unit volume, and then T we have thickness of the plate, and finally delta A is the area of the element. Basically T times delta A is equal to volume. Okay, we have area times thickness, we will get the volume. So and then this equation basically will use it to substitute in this formula, and finally we will get uh, this equation consists of gamma T A, and also consists of gamma T delta A. So we can make it a simplified equation, and finally we will have this, whereby gamma and T can be slashed out, and finally we will have this uh, x bar A equal to integration of x delta A. So in order to get the value of x bar, we will divide the integration x delta A to A. Then it's also happen to the moment at x-axis, whereby we substitute the value and finally we obtain the value of y bar is equal to such integration of y dA over A. And for the centroid of area, we will have a coordinate or x bar, y bar is something like this. So if we look at the centroid of line, okay, for the centroid of line, so we will substitute the value of weight force by using this value, whereby delta W is equal gamma A delta L, whereby A and delta L is a cross-sectional of a wire and length of the element respectively. And we substitute to this equation and finally we obtain the value of x bar is equal to integration x dl over A over L. So it also happened to the moment at x-axis, whereby the value of y bar is integration of y dl over L. So finally, this equation of centroid of a line is something like this. So if we compare three of the equation is something like this, whereby we have slightly the same but different in terms of the W. Okay, so W will, if you want to use a centroid of an area, so just change the W to A, centroid of the line, so change the W to L. So and then we proceed for the first moments of areas and line. So basically the first moment of area is very important in mechanics of materials for determining shearing stress in beam under transverse loading. Basically the value of first moment of A, which is area for the is represent by the QY, okay, whereby the value is basically x bar A equal to integration of x dA. So in terms of first moment of respect to x, we have qx. The value is y bar A equal to integration y dA. So in order to get the first moment at with respect to y, we call it qy. First moment with respect to x, which is qx. Okay, for the area of symmetry with respect to an axis of B prime, okay, in this case we have this shape, and this shape we have B prime, whereby the point P basically is a symmetrical point at P prime here, okay, at the same distance, is symmetrical with this line, okay, whereby this value is perpendicular, okay, this line and this line is perpendicular, okay, 90 degree here, and the length is the same, okay, but the coordinate is depend on the coordinate system, okay. So in case of this, okay, we have also this is the center uh, symmetric line. So if we have dA, this point dA, and then this is the mirror image of the dA prime at a certain length. If we have in the coordinate system whereby we have x and y, so this value basically in the negative side, okay. the first moment of an area with respect to a line of symmetrical is 0. And then we have if the area possess a line of symmetry, its centroid lies on the axis. Okay, if we can see from this rectangular, so there is a two line of symmetry which is from the x and y. So this basically is a line centroid basically in this line. Okay, this line or this line, but in this case the intersection is basically in this middle or in this, okay, middle. If an area possesses two line of symmetry, its centroid lie in their intersection. Okay, an area of symmetry with respect to a center O. Okay, in case of this shape, okay, center O in this coordinate system of x axis is at O and y is at O. Okay, if the point of this point at DA, so the O is a center, so it will every element of DA at this point we have x and y, so the axis of a DA prime at this point, so whereby the value of coordinate is negative side. So the centroid of the area coincide with the center of symmetry. So we have a line of a triangle is something like this. So this is the uh, centroid. So this diagram shows the centroid of common shape. Okay, previously I already show you the shapes, different shape with the centroid position, whereby in this diagram show a different type of common shapes together with the x bar and y bar value and also the area. This is the formula in order to get the x bar, y bar, and area. In terms of we have a triangular area, which is the centroid somewhere around here, whereby the value of B and H represent for the x-axis and y-axis. In terms of value of y, basically the value of H divided by 3. And for the quarter circular area and semicircular area, the value of can be seen through this formula. Okay, it's also happen to the quarter elliptical and semi-elliptical, whereby this formula basically quite the same, but the area is a little bit different. Okay, and it will represent by using A and B, okay, for the x and y axis. Okay, also happen to this shape of parabolic area, parabolic spandrel, whereby you can see this one is required for the function, okay, where y equal to kx squared. In this case, the value of kind of this triangle, okay, is something like this, okay, the centroid. Okay, if we see a problem related to the common shape, maybe we can use this formula to assist us in order to get the value of x bar and y bar. Yeah, this is the centroid of common shape of line. Okay, if as you can see, the centroid is basically outside from the line. So in order you to get the value of a quarter circle arc or semi circle arc or arc of a circle, you can use this formula. So and also the length. Okay, so we proceed to the composite plates. Okay, but basically the same explanation as a previous by using a concentrated or distributed uh, weight. Okay, and then represent for the concentrated weight as a W, and previously we have a delta W for the distributed weight, and act as a whole body by using a concentrated weight as SW. Okay, here we can see as a composite is a basically a combination of common shape. So once you have the composite plate, we will basically divide by a certain shape that is common, whereby we can use the formula from the common shape to solve this problem. Okay, basically if we have this composite plate, we can divide into several shapes here. Okay, in this case we have three shapes that we divide into three. The first one is uh, force produced by the weight of from the C1. Okay, and then we have C2, and then we have C3, where the value of W1, W2, and W3. So this is can be represented as a whole uh, body at this point G. Okay, whereby is the summation of all this value W1, W2, W3, and to be a summation of W. And it also happen to the value of X bar and Y bar. Okay, and finally we can summarize as a the moment at point Y or at Y axis is basically the value of the summation all together at a different point of G1, G2, and G3. So finally, we have the summation of a moment at y-axis is x bar summation of w equal to summation of x bar w. So in order to get the value of s bar, okay, this value must be divided by this value, and finally it will become something like this. And it also happen to the summation of moment at axis, and finally we will obtain the y bar is something like this. Okay, and for the composite area, okay, basically represent for the area whereby we use the same uh, formula as previous slide. So we just change the value of w to a. Okay, this also happen to the uh, lines. Okay, and if you can see differences between them, okay, whereby the value of area and line for the composite basically just change the w to a and l. Okay, let's see the problem one. Okay, this is the basic for the identifying the centroid. Okay, so as you can see, there is a rectangular with a different dimension of 45 at y value, and at x we have 72 mm. So in order to get this is very basic, just if we in order to get the value of the centroid, just make a symmetrical at x axis and y axis. Okay, so that is mean we just divide the value by 2 of each axis, and finally we will get the value of x bar is equal to 36 mm. For the y bar, we get the value of 22.5 mm. So this is a very basic. Okay, so in order to get centroid um, of a triangle or something like this, okay, in problem 2, so basically we will use a formula in a common shape in the previous slide. So basically in order to get the x bar and y bar, we just use the formula uh, for the triangle. We just divide the value of x and y axis by 3. Okay, and finally we have x bar is equal to 27 divided by 3 is equal to 9, and also y bar we have 15. So the centroid coordinate is 9, 15. Okay, it also happen to the all those common, so whereby we can use the formula to tackle this problem. Okay, but what happened to this shape? Okay, so we need to locate the centroid. Okay, it's plane area shown in this figure. So there are two ways to settle this problem. But firstly, we look at this the method number one, which is by using this kind of firstly you need to determine the area. Okay, you need to split the shape into two. Okay, for this first one is determine the area number one, whereby we have a bigger area uh, by using this the whole shape, whereby we have 45 by 72, and you need to minus this triangle. Okay, and by using this formula, so basically by using the technique, but you for the systematically calculation method, we will make it using table, something like this. So the table area number one, basically at point number one here. So the rule here number one, okay, we have 5 column indicates a value of a, x bar, y bar, x bar a, and finally we have y bar a. So this is in this formula. So by using this table, we will make easily to calculate and very fast to get the value. So in terms of area A, so we have the value of A, basically the area. So we have 72 times 45, we have 3240, and the x bar and y bar, basically we already can get the value by using the symmetrical value. So the x bar is 36 and y bar is 22.5 from the 45 divided by 2, and the x bar a, okay, we have the value of x bar 36 times 3240, and it will come this value, and also y bar a from the value of 3240 times 22.5. And it also happened to the area number 2, whereby this area number 2 we need to subtract the value. So the area of triangle basically 45 times 27 divided by 2, the area, and we have this value. So we need to subtract the value, so we put the negative value. So an x bar basically by using the formula we already done previous slide. So 27 divided by 3 and 45 divided by 3, which is 9 and 15, and multiply all together, and finally we obtain this value. So and then we need to get the summation of all a area and all this value and also this value. Okay, by using the formula, and we substitute the value in the formula, and finally we obtain the value of x bar, which is 42.23 mm, and also we have y bar is equal to 24.23 mm. Okay, this is the location or the coordinate for the centroid of the shape. Okay, and if you want to use a second method, which is by using this area, okay, and also uh, add additional to the area number 2, which is using a triangle. So you can also calculate by using this technique. And then we have problem number 4. This one related to several shapes. So we need to first to obtain the first moment with respect to x and y axis. Okay, and then try to get the location of the centroid. Okay, basically we will have basically we will divide by 4 shapes. Okay, which is the shape number 1 is a rectangular, and then for the shape number 2 is a triangle, and then we have a semi-circular. This is we sum all together and minus or subtract this circle. Okay, basically we need to put all together in table, so that is very easy as to calculate and quite manageable to very systematic in terms of getting the result. So we will proceed to the first shape. Okay, basically we have a rectangle. We calculate the area. Okay, and then we try to get the x bar and y bar. Here basically the shape, all shape is in the coordinate system, so you cannot simply get the value of symmetrical shape x bar and y bar, but you need to include the uh, coordinate system. Okay, okay, in this case we have 40 mm for the y bar, and for the x bar we have 60. Okay, this one is 120 divided by 2. Okay, we obtain the value of 60. Okay, and then you calculate the value of x bar a and y bar a. It's also happened to the triangle. So in this triangle, basically the centroid is in the negative side of y value. For the x value is positive. So you need to calculate by using formula all value divide by 3. So in this case, we have x bar is 120 divided by 3, we have 40. And then the y value is 60 divided by 3. It will produce 20. So the y is in the y negative. Okay, y axis is in the negative side. So you put a negative value. And then you calculate the x bar A, y bar A. And it also happened to the semicircle, whereby the semicircle given the r radius is 60. So by using a formula whereby the x bar for the semicircle, basically if the semicircle is in this xy position, basically x value is 0. Okay, for the y value is by using the 4 divided by 3 pi r. Okay, in this case this x bar value is 0, the y bar value is 25.46 mm. Okay, substitute of radius is equal to 60. So but this value you cannot put in the in this table. Okay, you need to include the actual position of the coordinate system here. So you can see here the semicircle is a little bit higher. It is not in the position of 0. So in case of the x value, maybe you can divide by 2 the value of 160. 120 divided by 2, you get the value of 60. So x is 60. So you put here. So in case of y bar, you cannot put the value 25.46, but you need the value of 45.246 is somewhere around here. Okay, so you need to add the value of this. Okay, which is 80. So 80 plus 25.46, you obtain the value of 105.46 here. So and then you get the value a bar, x bar A and y bar A. Happen to the circle, okay, whereby is the given circle radius is 40 mm, and can simply calculate the value. So you need to include the original position of circle, whereby the circle is not in the axis. Okay, so at a certain higher at 80 mm, and for y axis, and for the x axis we have 60. So and then please remember that the circle is used, we need to subtract the value. So you need to put the negative value all the value once when you calculate of x bar A, y bar A. So and then finally we will sum all together the value of A, area, and then sum together of value of x bar A and y bar A. Okay, and then we have this value in order to get the first moment of with respect to the y-axis and x-axis. Basically for the q y, basically the value is here. So for the qx, the value is here. So just take the value and put the value all together, and finally you get the first moment. Okay, for the determining the centroid location, so we will use this formula. So you substitute the value. So, and finally we will get the value of x bar is equal to 64.8 mm, and finally for the y bar, the value is 36.6 mm. So at the final position, if we put in the coordinate system, we have the coordinate is somewhere in this diagram. Okay, and the final problems, which is related to the location of centroid in the plane. Okay, final one is we have a wire. Okay, its band is something like this in red color here. So we have a dimension of it's not symmetrical, but we need to locate a center of gravity of this wire. Okay, so we need to use the same uh, formula, but we just substitute the a value to this one is wire. We substitute by using the L value. So basically, we have five wire attached all together to make this shape. So we will start from the wire number one. So you need to calculate the length of wire number one by using the dimension given, but which is you need to use a Pythagoras theorem to get the length. Okay, so we get the length of wire number one is 26.833. For the x bar and y bar, basically we just divide 24 from the x axis by 2, and we obtain 12. And also for the y axis of 12 here, we divide by 2 and we obtain 6. And we proceed to get the x bar L and y bar L. And it is also happen to the wire number 2, whereby we have the length is 32, and we put 32 here. And for the x bar and y bar, basically the x position basically for the this wire, okay, somewhere in the middle here. So 30 for the 32 divide by 2, we have 16. So here is 16, from here to here is 16. So the wire is in the coordinate system, so you need to take into account this height 12. So 16 plus 12 is 30. 28. So 28 for the y value, and for the x value is a position from here to here, which is 24. And you calculate this x bar L, y bar L. And it's also for the wire number 3, which is 42. This is you divide by 2. Okay, basically is somewhere in the middle, and you need to uh, get the value of x, which is 3, and for the value of y, so you plus all together 32 and 12, we have 44. And also for the wire number 4 here, and the position is basically at x direction is negative, so we have negative 18 according to this length 18, and then for we have 28, the same as the height. Okay, and finally obtain for the project number 5, and this value we proceed to get the L XL, X bar L, Y bar L, and finally we will sum all together of L. We get the value of 154.466, and also X bar L and Y bar L here. To get the value as X bar and Y bar, we substitute the value into the formula, and finally we get the center of gravity is X bar is 2.88 and Y bar is 225.4. So I think that's all for the explanation of how do we compute for the problem to get the center of gravity and centroid for the area and wired or line. So for the exercise number 1, this is the shape. So this is given the value. Okay, so try to get the answer. And also for this one, okay, different shape. So basically we will divide by using the common shape and by using its formula. Okay, uh, and also this one and this one problem related to the wire. Okay, and if you there are many things that the shape that is not a common shape, like a curve with the function of something, like y equal to x squared, x cube or something like this. So if we have a different very complicated shape, so we cannot use this kind of things to settle this problem. Okay, we will use a different techniques. Okay, so in next video we will produce a part B, whereby we can use the other technique to settle this problem related to different complicated shape. Okay, uh, but in 2D. Okay, and later on in part C we will try to solve this problem by using a 3D. Okay, so I think that's all. Thank you very much. Bye bye.